So we were talking about parameter substitution in the last class. So in particular, I was showing you a bunch of parameter substitutions that you can use with strings. So for example, removing the leading part of a string by matching a pattern, or removing the trailing part of a string by matching a pattern. What you have to be careful with is that the pattern matching that you get in parameter substitution is very primitive. It often does not do, or is often not capable of doing what you want it to do, right? So, for example, suppose you were given the problem, write a bash script that trims a string of all leading and trailing white space, right? So if you type in a string that's space, 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 ABC, space, 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 you want to get rid of the space at the end, beginning and end of the string. And you might think, well, I can just use one of these patterns here, or one of these, string hashtag pattern to remove the spaces at the front of the string, right? Because when you look at what this thing says it does, it says it removes the longest leading part of the string that matches some pattern, right? So you think, well, I mean, a bunch of spaces, I can just match, the pattern would just be a space, and it will remove all the spaces at the front and end, right? And so that would be what you would probably guess would happen if you didn't actually try it, right? So let's write a little script called trim.sh. Sorry, let me just crank up the font here so you can actually see. Shift, does that work? Yes, there we go. Okay, so I'm going to write a little bash script that trims the or I'm going to try to write a bash script that trims the leading and trailing space from a string, right? So remember, start of the script is always hashtag ! root bin bash, right? Or if you're on a Mac, /user bin environment, right? Bash. Okay, so this is going to be, trim.sh. It's going to trim leading and trailing space from a string, printing the trimmed space, the trimmed string to standard output. Okay, so the way this script's going to work is you're going to call trim.sh, pass it in a string on the command line, and then trim the string, right? So just get rid of the leading and trailing space. So S is $1, $1, right? First command line argument, that's going to be the string to trim, right? Now, you go and look at that notebook that we had, and you say, well, I can get rid of the longest part of the front of the string that matches a pattern using hashtag, right? So in other words, I can get rid of all the spaces from S by writing something like that, right? So S, that's the string to trim, right? Hashtag, get rid of the longest leading part that matches a space, right? You say, okay, that looks promising. So now I've gotten rid of all the spaces at the front. How do I get rid of all the spaces at the end? Well, that's just a different symbol, and I think it's %%, like that, right? So get rid of the longest part of the string at the end that matches the space, right? So you think, well, that's going to get rid of all the spaces at the end, and then print the string. And so echo $T. Now, I'm going to put it in quotes just to make sure, in case there happens to be any space at the front or the end of T. And I'm going to do this, right? So I'm going to print out underscore and then the string T followed by an underscore, so that if there is any space still left at the front of T, front or end of T, we can see it easier, right? And I guess for the purposes of debugging, I'm going to echo S in the same way. Right, again, so this is just for the purposes of debugging so that we can actually see what our inputs and outputs are. Right? So you try that and you look at it and you say, well, yeah, that looks reasonable. And so you try it in, in your shell. Okay, so let's make sure that trim is here. It is. Right? Let's make sure that trim is executable, and it is, right? So I have execute permission on that script, right? So I can run the script. So dot trim sh. Okay, ABC. So there's no string, there's no space at the front or end of that string. I should just get back the string ABC, and I do. Right, so that looks promising. Now, how do I enter in a string with spaces in it? Right? Well, I have to quote it, or I have to escape the spaces. So let's try a space at the front and the end of the string. Looks good, right? The input string, right, has a space there, and space there. Output string, oh, wait a minute. What did I do? Oh, so the output string, sorry, something must be wrong with my script. Hang on. Echo S $. Hashtag, hashtag, right? That's the longest, oh, yeah, longest leading part of the string. Yes, that matches the space. Okay, so echo S, and that's there, hashtag, hashtag, and there, and then, oh, haha, sorry, T, there we go. I thought there was something wrong. Okay, so T, so I'm going to remove all the leading spaces. I'm going to try to remove the leading spaces from the front. Sorry, I'm going to try to remove the leading spaces from S. Then I'm going to try to remove the trailing spaces from T. Okay, so that's better. So let's run that again. Let's make it a little bigger so you can actually see. Okay, there we go. Okay, so that looks promising, right? Space is gone. Space that was here and the space that was here is now gone. Run it again. So add an extra space, and oh wait, there's a space here, right? And there's a space here, right? So in fact, it's not doing what you think it ought to be doing, right? So again, let's go back in our script and see what's going on, right? So I'm using this syntax here to remove the longest part of the string that matches that pattern right there. So that pattern is just the space, right? So the longest part of the string that matches one space is always going to be at most one space, right? It doesn't actually remove all the spaces, right? It only removes the thing that matches this, right? That's a space. So the longest string the longest part of the string that matches a space is always at most a space. Similarly here, the longest part of the string that always matches the space is a space. There's no way to say I want to match an arbitrary number of spaces with this particular construct, right? There is a way to do it, but you have to use something else, right? So with these sort of substitutions, or expansions, I guess, the pattern matching is very primitive, right? It literally matches whatever's here, right? So the only thing that can match is a single space. So if you put in more than one space, it only gets rid of a single space each time. Right, so that's not going to work if we actually want to write this script called trim.sh. Right, so for that, we need something else. All right, so that takes us to the next notebook, which is called the tr command. So tr is a command that translates squeezes or deletes characters from a string using a sequence. Right? So the way you use it is tr, right? Then you've got whatever options that this tr command takes. And then you have sequence 1 and sequence 2. Right? So sequence 1 is a sequence of characters to convert from. And sequence 2 is an optional sequence of characters to convert to. All right? Now, tr is funny. It reads its input from standard input. So let's take it out for a spin and see what happens. Okay, so tr, I need a sequence. So I'm just going to say a. And for every a, I'm going to replace every a with a z. Okay, so this is what this version of tr is going to do. Right? For every a that's on standard input, replace that a with a z. All right? So now I have to type something in on standard input. So aardvark. Enter, right? So it takes every a, and replaces it with a z, right? So ZZ, RD, V, ZRK, right? If I type in something like, that doesn't have an a in it, like Erie, right? It just passes each character through unchanged, right? So in other words, tr looks at your string, converts each character of a string by looking at this set here and replacing it with the corresponding letter from that set there, right? So let's look at a different example. Okay, so I want to replace A, B, and C with X, Y, and Z, right? Okay, so let's try aardvark again. Okay, so this says replace every A with the corresponding letter in the second sequence, so with X. So this should do XXRD, right? If you do bat, right, so that's going to replace the B with a Y and the A with an X, right? And I guess if you do cat, it's going to replace the C with a Z and the A with the X, right, like that. Control D will end your input, will stop standard input, right? So that'll stop the TR command. All right, so that's the simple way of using TR, right? So that's straightforward translation from one set to another. Now, if you want to use this in a script, you don't want to be reading standard input all the time, right? Sorry, wrong. Okay. So TR takes its input from standard input. So this is one of the commands that does read standard input, doesn't read from a file or a string. So if you want to use this inside of a script somewhere, you have to print the string that you want to process and pipe that string to TR, right? So I've got the string X sparring with a purple porpoise again, right? I would like to replace all the P's with a T, right? So I know how to do that with TR. I can just write something like that, right? Replace each P with a T. Right? I don't want to read from standard, well, I don't want to type in the string sparring with a purple porpoise on the keyboard. So instead I print the string. So here I'm using printf. You don't have to use printf, you can use echo here. Right? So printf says to print its argument, so this is $x, as a string. Right? So that's what the %s means here. It means print the argument using it as a string. Right? Right, so that will print my string to standard output, right? Standard output gets piped to TR, right? And I can store all of that result in the variable y, right? So here, right, everything's inside round brackets, right? So I'm using a command substitution here, right? So remember, a command substitution takes the output of a command or pipeline, right, and substitutes that output for that expression right there. Right? So the dollar round brackets, run the command inside the round brackets, and then replace all of that dollar round bracket stuff with the output of the command. Right? And so if you actually run this, you get starring with a turtle tortoise. Right? So that, in fact, will replace every occurrence of P with a T. But we already know how to do that using a parameter substitution. Right? So there is a way to do that just directly from the string itself. So you don't actually have to do this using TR in this example. Right? Okay, here's another example. I want to replace every occurrence of a period with a slash. Right? Probably shouldn't be showing you this example because this is an assignment solution, actually. Was this assignment 1? I don't remember if this is assignment 1 or assignment 2. Is it 2? Well, here you go. Here's the answer to assignment 2. Right? So you've got a string. You've got the string equal to a Java package. Right? So that's the fully qualified Java package name. If you want to get the name of the directory corresponding to that package, well, you can just use tr. Right? Or you can just use a string substitute. You can just substitute a character in the string. Right? Using, I forget what substitution is. No one remembers what all these symbols are. You have to look it up all the time. Right? Okay, so you just use // instead. So you can use this construct as well to solve the same problem. Right? All right. So what else can this thing do? Well, when you specify the sequences, you don't have to, one way is just to type in the letters, right, of both sequences. So you can use a string for your sequences, right, which is what I did when I showed you how to use it the first time, right? But there's other things you can do as well, right? So you can specify a range instead, right? So A-Z is the letters A through Z in alphabetic order, right? So that will also let you define one of the sequences, right? And then you can also use the POSIX character classes, which we saw earlier, right? So square bracket, colon, upper, colon, square bracket, right? That's all of your uppercase letters. So for example, right, here's the string CISC220, right? I would like to capitalize CISC, right? So I can take the sequence of letters A through Z, right, and replace those with the uppercase letters A through Z, right? So this works for any string. It doesn't work for just CISC220, right? I can do this for any string now. Right? So the lowercase a gets replaced with uppercase a, lowercase b gets replaced with uppercase b, and so on and so on and so forth. Right? And so this one, when you run it, not surprisingly, produces CISC220, right, in all caps. Right? Now, what happens if your sequence 1 and your sequence 2 have different lengths? Right? So remember, it's going to do character, it's going to take the character, it's going to find a character in sequence 1 and replace it with the corresponding character in sequence 2. So if sequence 1 is shorter than sequence 2, then there's no problem, right? The excess characters of sequence 2 are simply ignored, right? So it's the exact same example, except sequence 2 now has 0 through 9 here. These spaces aren't here. I was just farting around earlier. So A through Z, and then 0 through 9, right? So A, B, C, D, E, F, G up to capital Z, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So sequence 2 is longer than sequence 1. Not a problem, right? Just ignore the 0 through 9, and you get the exact same result. The problem occurs when sequence 2 is longer than sequence 1, right? Sorry, when sequence 1 is longer than sequence 2, right? So you've got more characters that you want to replace than you have replacement characters, right? And so in this case, the behavior is actually undefined. So if you take your script from to a different operating system, to a different POSIX operating system, then you might get a different result. Right? So in bash, if sequence 1 is longer than sequence 2, then sequence 2 gets extended by copying the last character of sequence 2 until sequence 2 has the same length as sequence 1. Right? So in bash, this script here works. Right? So here I've got CISC220. I'm going to try to replace all the digits, right, 0 through 9, with X. Right? So now sequence 1 has 10 characters in it. Sequence 2 only has 1. Right? In bash, that X gets duplicated out so that it becomes 10 X's. Right? So when you run this, this actually works. Right? It replaces all the digits with an X. This only works in bash. If you take it to a different shell, there's no guarantee this will work. If you really want this to be portable, then you should use the very strange syntax that looks like this. Right? So inside square brackets, if you write X star, that will duplicate X enough times so that sequence 2 becomes the same length as sequence 1. Right? So this one is explicitly saying, hey, duplicate X so that it has the same length as sequence 1. So this one is portable. Right? And it does the same thing because this is bash. Right? Okay. Now what happens if you have duplicated characters in sequence 1? Right? Duplicated characters in sequence 2, it doesn't matter. Right? So if you have A, B, C, and that maps to XXX, then A and B and C, they just get mapped to X. Right? Here, I've got C, I, S, and C all lowercase. So I've got a duplicated C. Right? A duplicated lowercase c. So the question is now, what does TR do? Right? And so the documentation actually says the result is undefined. Right? Here, on this particular version of Linux, with this particular version of TR, in this particular version of bash, right, what ends up happening is something somewhat unexpected. Right? You end up with big CISS220, right? Which is very weird, right? So why would that lowercase c, right? Why does that get mapped to an S? And the answer is, who knows, right? The actual answer is because bash duplicates that S, right? It duplicates the last character of the second string, right? So that it's longer. This isn't bash, sorry, this is TR. So this version of TR duplicates the last character so that so sequence 2 has the same length as sequence 1. And now when it does the replacement, right, so when it sees the C, it's using the last instance of C in this string, right? So now it's matching that C to the capital S, which is why you get big CISS220, right? So that's what's going on in that example. Very unintuitive. I guess the moral of the story is make sure your strings have the same length, right? Or make sure that your second string is longer than your first string, right? Okay. You can use tr to delete characters as well, right? So if you use -d as your option to tr, that tells tr to delete characters that occur in that sequence. Why did I write sequence 2? That is a bug. That should be sequence 1. Sorry. So if you have fix that bug in your notebook. That should be sequence 1. Okay. So any character that occurs in that sequence will get deleted from the string. Right? So here I've got 2022 hyphen 10 hyphen 21. Right? I want to delete all instances of the hyphen. Right? So I can use tr to do that. Right? I just use -d, and that will delete all instances of the hyphen. Right? And so there you go. That removes all instances of the hyphen from the string. Right? So this is how you would use tr to trim the leading and trailing spaces from a string. Right? You can that sequence there would just be a string. It would be the space, right? And you would use tr -d to delete all spaces. Now that almost works. It doesn't quite work. Anybody see why that doesn't quite work? It does in fact delete the leading and trailing spaces, but it deletes something else, right? It deletes all the internal spaces as well. So using tr doesn't quite solve our problem either, right? So in other words, if you try to use tr in your trim command, you end up deleting everything from the string, or you delete all the spaces from the string, right? Tr has no way to know, there's no way to tell tr to delete the trailing or leading spaces, right? You can delete them all, but you can't delete just the ones at the front or just the ones at the back. So that doesn't quite solve our problem yet either. Finally, you can use tr to remove repeated characters. Right? So the -s option will squeeze repeated characters that appear in the set sequence 1. Right? The repeated characters are replaced with a single instance of the character. Right? So here I've got a bunch of spaces. A bunch of repeated spaces there. I've got a bunch of repeated spaces here. Right? If I want to get rid of those repeats, well, I can use the -s option. Right? And my sequence is just a space. Right? So in other words, replace all instances of 2 or more spaces with a single space. Right? So when you run that, right, you get A, 1 space, B, C, D, 1 space, E, F, 1 space, G. Right? And so there's the tr command, which is also useful, which does some things that your regular parameter substitution with strings can't do. Right? All right. I'm going to jump ahead a few notebooks so that you can actually do your assignment. So I'm going to jump ahead to conditional statements. Right? We'll come back to the other ones shortly. So in your assignment is basically string manipulation, command line argument manipulation, and if statements. Right? That's more or less what you have to do. There's a little bit of arithmetic, but arithmetic's pretty straightforward in Bash. The if statements are a bit odd in Bash. Sorry, I should have loaded this notebook before I came to class. Okay, here we go. All right, so Bash does have an if statement. The overall structure of the if statement is not terribly unusual, right? So it's if, and then something here, right? The something here is the weird part. Semicolon, right? Then, right? So if whatever this is evaluates to whatever Bash considers to be true, right? Then these commands happen. Right? Now there is no, the else if part is ELIF in Bash. Right? Then something here and a semicolon, and then, sorry, and then, right? So if these commands are true, so if this evaluates to false and this evaluates to true, then these commands run, right? And then the else part's just else. To end the if statement, it's fi, right? So if in reverse, right? So phi ends the if statement. The semicolon, so this is the way I normally write it. There is another way to write it. Do I tell you? Yes, right? So the other way to write it is like this, right? So if some command here, then, right? Else if some command here, then, right? So if you put it on the separate line, you don't need the semicolon, right? Now, the weird part in bash is that what you want to be a condition, if you come from a language like Python or Java, right, is actually a command, right? So you're going to use the output of a command as the condition for your if statement, which is bizarre, right? So the unusual feature of the bash if statement is the use of commands as the test condition, right? Okay, so remember every command has an exit status, right? The exit status is 0 if the command encountered no errors, right? The exit status is non-zero if the command encountered some error, right? So an if statement, you can use the exit status of a command or commands, so an entire pipeline if you want, as the condition, right? So that condition right there can be a command, right? So you can write if ls or something like that, right? Some bizarre thing like that, right? The command runs, right? If it generates output, the output gets printed to the terminal, right, or to standard output. If it generates an error, the error gets printed to standard error. And then the exit status is used to determine whether or not this happens. Oh, sorry. Whether or not this happens, right? So run the commands. Look at the exit status of the command. If the exit status is 0, then this runs. If the exit status is not 0, then that does not run. It goes to the else if part, right? Another command, right? If the exit status of that command is 0, that runs. If the exit status is not 0, in other words, if it encounters an error, then it doesn't run, right? And so on and so on. Okay. So in bash, there's a command called, sorry. Okay, in bash, there's a command called true. So when you write the word true, that's not a bash keyword. That's actually a bash command, right? So the command true does nothing but set the exit status to 0. Right? The command false does nothing but set the exit status to non-zero. I think it sets it to 1, right? So this says it sets it to 1, right? So true and false are not actual keywords in bash. Don't use them for this purpose, right? So be careful with that. That's why that cell's in blue. Okay, so here's an example of when you might, of using a command as a condition, right? So this one is change directory and then list the contents of the directory if the directory exists, right? So cdls, right? So you cdls some path name, right? If the directory exists, it will change to that. Oh, I guess if the directory exists, is readable and executable to you, it will change to that directory and then list the contents of that directory, right? So how would you write this? Well, one way to write it is with an if statement, right? So if I can change to that directory, right? So if that succeeds, right? In other words, so if that succeeds if the directory is readable, exists, sorry, if the directory exists, is readable and executable to the user, right? So if that exists, if that works, then go ahead and run ls, and that will always work, right? If that doesn't work, then we print an error, right? So here I'm printing an error, and I'm going to send that error to standard output, to standard error, which I don't think I've shown you how to do yet. So echo sends its output to standard output, right? If you want to take that output and instead send it to standard error, you write that at the end. Sorry, you write that at the end, right? Sorry, one more time. You write that at the end. So greater than and 2, right? And so what this does, this actually copies the file descriptor belonging to standard output to the file descriptor belonging to standard error, right? And so what this does is it takes whatever would normally go to standard out and redirects it to standard error, right? So the greater than sign, that's redirection, and to means copy whatever went to standard error to standard, whatever would normally go to standard output to standard error, right? So that's handy, right? So whenever you want to print an error message, that's the way to do it, right? Or this is one way to do it. And then we exit with a non-zero status here to indicate that our command failed. Right. Okay, so you can actually run that script, right? So if you ask cdls to change to the current directory, that will always work. I guess I have to run that other, hang on just a second, I have to switch into that, oh, I didn't tell you to switch into that directory. Well, this is going to fail. Sorry. I have to, oh no, this is work. Okay, this will be fine. I put in the full path name of the directory. Okay, so change to the current directory and list its contents. No problem, that should work. That works, right? Okay, change to this directory, which definitely does not exist, right? Because that's root/bad_dir name, right? And there's definitely no directory called bad_dir name in my root directory, right? So this is going to fail. So when you run this, right, you get your error message here, right? You also get the error message from CD, right? So notice right here, right? CD is complaining that CD's bad_dir name, no such file or directory, right? So if you go back and look at the script, right? When that command runs, whatever output that command generates, right? It still generates that output. Okay, so that's a bit weird. So using the result of a command as a condition is one of the odd things that you can do in Bash, right? It's a little unusual to do. Now, normally you want something that actually looks like a condition. And so there's several ways to do this. The old way to do it, the old and portable way to do it is with single square brackets, right? So I'm going to show you, I'm not going to show you the single square bracket construct, right? This is how you would use, this is the most portable way to do it. So basically every shell understands the single square brackets. In Bash and other newer shells, they understand the double square bracket construct. And so that's the one I'm going to talk about. I'm not going to show you the single square bracket. The single square bracket one looks a lot like the double square bracket one, but there's a lot of rules you have to remember. So the double square bracket one is generally easier to use. The double square brackets also works in Z shell, which is your Mac shell. Right? Okay, so the way this thing works is it's double square bracket, and there's some expression inside the double square brackets. Right? Now, the expressions that you can write, there's a finite number of them. So I'm going to show you what those are in a second. Right? So this construct here is actually a command, believe it or not. Right? So the square bracket is actually a command in Bash. So the double square bracket, Bash interprets as a command. Right? That command evaluates to 0 if expression is true. It evaluates to 1 if expression is false. Right? So that's why you can use this as the condition for an if statement, because it's actually a command that sets the exit status to 0 or 1. Okay, now notice that there's a space here, right? And notice that there's a space here. Okay? So those spaces are intentional. They have to be there. Right? That's why the yellow box is here. Right? There's the space before and after the logical expression is required so that Bash can correctly parse that construct. Right? If you don't put the spaces in, Bash will complain. Right? It may not complain. You'll get some odd errors. Right? Space has to be there. So don't forget the space. All right. The nice thing about the double square brackets is that word splitting and file name expansions do not occur inside the double square brackets. Right? So you don't have to worry about word splitting. So what does that mean? You don't have to worry about quoting your variables inside the double square brackets. That's nice. Right? No file name expansions occur. Right? So you don't have to worry if a star or a question mark or a dot appears in your variable. Right? They won't get expanded. The file name expansion does not happen. Right? And that makes using double square brackets a lot easier. The single square brackets, that's not true. Word splitting happens, file name expansion happens, and you have to be careful about quoting every time you use the single square brackets. All right, so what kinds of expressions can you use? So broadly speaking, they fall into 5 different categories. Right? There are some miscellaneous expressions. Actually, I think there's only one, right? Yes, there's one. There's one miscellaneous expression. Right? There's a bunch of expressions that work with files. Right? So you can test, does a file exist? Is a file a regular file? Is it a directory? Is it readable? Is it writable? Is it executable? Right? So all of those things, there's a special construct. There's a special, there's a special way to write those expressions. Right? There's a bunch of string expressions. So you can compare strings for equality. The double square brackets lets you compare strings in another special way that we'll talk about next class. There are integer expressions. So you can compare integer numbers. Right? So there's a way to test, is a variable equal to 1, for example. And the regular expressions, we'll talk about those in the next lecture. Right? So the table below, I'm going to show you the most commonly used ones. They're not all of them. There are other expressions that you can use. The link takes you to the official documentation to all of the expressions that are usable. Okay, so the expressions look a bit odd. Right? So minus v followed by some variable name, right, is true if that variable name has been assigned a value, right? So it's true if that variable name has been assigned a value. So that's useful if you want to know, has a variable been set yet? That's the only miscellaneous expression that I'm going to talk about here, right? The file expressions. So these are the ones that work with files, right? So minus d followed by some file name, right? If that file name is a directory, then that's true, right? If the file name is not a directory, then it's not true. Right? Minus e, does the file exist? It's checking purely for existence, right? Could be a file, could be a directory, could be a character special file, or something like that, right? Could be a link, could be a soft link, right? So minus e followed by the file name, does it exist? Right? Minus f, is it a regular file? Right? So like a text file or some other type of file like that. Not a directory. Is it readable? Right? Minus w, is it writable? Minus x, is it executable? Right? Minus s, is the file size greater than 0? Now, if you want the opposite condition, right? Is the file not a directory? Right? Then it's exclamation mark space minus d file. So the exclamation mark is not in bash. There has to be a space between the exclamation mark and the hyphen, right? So exclamation mark, not, right? That's negation in, that's logical negation in bash. Okay, you can compare 2 files by their modification time. So this is handy, right? Is a file newer than another file, right? File 1 hyphen nt file 2. Is file 1 newer by its modification time than file 2? Right? OT is older than, right? So is file 1 older than file 2 by its modification time? All right, the string expressions. If you just write a string, so the name of a string, or the name of a variable right? Then that returns true if that string is not empty, right? So if $s, for example, returns true if the string s stored in s is not empty. Minus n string, the length of is true if the length of the string is greater than 0. Right? Minus z string, the length of the string is 0. Right? String 1, so if you want to compare 2 strings for equality, it's either equals or equals equals. Both work in bash. Right? So equals or equals equal, those are both string equality. The next one we'll talk about in the next lecture, right? Equals tilde. So this does what's called a regular expression match. Exclamation mark equals, not equals. Right? Greater than, does string 1 come after string 2? Right? Less than, does string 1 come before string 2? Right? Now the integer expressions you can also use. I don't recommend you use them. it's easier to use an arithmetic expansion to calculate these, right? But if you want to use the square brackets, you can, right? So some integer value minus EQ, some other integer value, test if they're equal, right? Minus NE is not equal, right? Minus LE less than or equal, right? No, you can kind of guess what these are all going to be, right? All right, so I recommend, so you can use these if you want to, there's nothing wrong with it. It's probably easier to use an arithmetic expression here instead, right? Because then you can use the greater than or the greater than equals or the less than or less than equals, right? You don't have to remember what these all mean. Okay. So now we've got a bunch of examples that go through a lot of these, right? So when you're using a minus v var name, that tests does the var name have a value, right? You have to remember that var name is the name of a variable, right? Do not use dollar to get the value of the variable, right? So you're not dereferencing the variable. You're asking, does the variable have a name, have a value, right? Okay, so here I've got this command that says unset x, right? So the bash built-in unset, right, unsets the variable x. So in other words, if the variable x exists, then unset x effectively deletes the variable x, right? If x does not exist, it doesn't do anything. X doesn't exist still, right? So here I'm just using unset x in case you come back and run this cell later on and you've already assigned a value to x, right? Okay, so minus v, has x been assigned a value yet? Right? Apparently not, right? So minus vx, does x have a value? If so, print x is assigned, otherwise print x is not assigned. So this prints x not assigned. Now, if you comment that out and run this again, it's going to print x is assigned. Oh, it's still x is not assigned. Okay, good. So it doesn't do what I thought it would. Right, okay, good. So that does what I was hoping it would do. It's going to be in the next cell, so here. Okay, so here, I assign a value to x. Run it, and it says x is assigned, right? If you go back up to here, it's still going to say x is assigned again, right? So in other words, when you're running these cells in a notebook, they're all running in the same shell, right? If you assign x in one of your cells, it's going to be assigned, that variable x now exists. That's why the unset x is here. Right. Okay, some file expression examples. All right, so files are basically, files and strings, those are the two fundamental things in a bash, right? So it's not surprising that there are expressions that are created especially to work with files, right? So here we go. Okay. Now, also remember that when you're working with file names, right, if your file names have unusual characters in them, like spaces, stars, question marks, right, then normally what will happen when you use a variable, right, that stores one of these weird file names, you'll end up with word splitting and file name expansion happening to the variable, right? That's really inconvenient, right? So when you look at a lot of bash scripts, all the variables are double quoted, right? Or many of the variables are double quoted, and that's to prevent word splitting, file name expansion from happening. Inside of square brackets, double square brackets, sorry, you don't have to worry about word splitting and file name expansion, right? So inside the double square brackets, you don't have to quote your variables. Right? Okay, so this little script here, it's just going to run a bunch of if statements, right? If the file exists, right, then if the file is a regular file, it's going to print it's a regular file, right? If the file is a directory, it's going to print the file is a directory. Right? If the file is readable, it's going to print it's readable, right? And so on and so on and so on. Right? Okay, so if we run the script, right, there's a file called scripts in this directory, right? So scripts is a directory, right? Scripts is readable, it's writable, it's executable. If you're wondering what scripts is, it's the following. Come on. Sorry, hang on. Okay, so if you're wondering where scripts is, so that notebook is running in this directory. So that is that notebook is conditional statements, right? So that notebook's running in this directory. you can see that there is a file called scripts, right? That file scripts is a directory. Right? It's readable, it's writable, it's executable, because that's where all your scripts are for the notebooks, right? Okay, so the notebook for this, the notebook name for this notebook is conditionalstatements.ipynb. So if I run that script on that notebook, it tells me it's a regular file, it's readable, it's writable, right? Finally, one more, right? If there is no such file, so this script prints no such file does not exist, right? So it's pretty straightforward using the using the file expressions, right? Again, if you want the opposite of something, so if I want to know if something's not a directory, exclamation mark space minus D, right? Is it not a regular file? Exclamation mark space minus F, right? Does it not exist? Exclamation mark minus E, right? And so on and so on and so forth, right? I really should have put one of those examples in the notebook, but anyway. Just remember that the exclamation mark is negation in bash. All right, so I think that's enough for today. We'll still end it there, and we'll finish off this notebook in the next class.